Today we are going to study trigonometry. It is another branch of mathematics that deals with the properties of a triangle and their applications. Trigonometry. Trigonometry deals with the properties of a triangle and their application. A triangle is a plane shape bounded by three lines. Here is an example. You look at this triangle here. This is called a right-angled triangle. This angle here is 90 degrees. Hence, the name right-angled triangle. The other two angles by the arcs used to describe them are equal angles. It therefore means that this triangle has another special name, and that is called an isosceles triangle, which I deal with more of that later. The second one here is an obtuse angled triangle. Obtuse angle because this angle is more than 90 degrees. The others are acute angles, less than 90 degrees. But this type of triangle, in which the angles are not equal, is also called a scaling triangle. In other words, the sides are not also equal. The third one is an acute angle triangle, which means that all the angles, the three angles, none of them is more than 90 degrees. They are each less than 90 degrees. And such a triangle is called an acute angled triangle. We have other types of triangles like the equilateral triangle, in which all the angles are equal and all the sides are equal. We shall be treating some of them as we go along. Trigonometric ratios of a right-angled triangle. Here is a right-angled triangle, lettered A, B, C, and then an angle theta. The side A is the side that is opposite to the angle theta. You can see the theta, this side is opposite it. The side B is the side that is adjacent to the angle theta. You see the line here is adjacent to this angle. And while the side C is equal to the side opposite the right angle. This is opposite the right angle. And it is called the hypotenuse. It is the longest side in a right-angled triangle. The basic trigonometrical ratios are the sine, cosine, and tangent. And they also have their reciprocals. And their reciprocals are the cosecant, secant, and cotangent, respectively. In other words, the reciprocal of sine is cosecant, and the reciprocal of cosine is secant, and that of tangent is cotangent. Sometimes shortened as follows: sine, we have cosec; cos, we have sec; tan, we have cos. We have the definitions of sine, cosine, tangent, and their reciprocals. These are the tools we are going to be using in dealing with problems involving triangles. So their definitions with reference to the right-angled triangle above are: 1. Sin theta is defined as opposite over hypotenuse, and with reference to the triangle we have above, that is A all over C. Cosec theta, the reciprocal of sin theta, is the inverse of sin theta, which is hypotenuse over opposite, which is C all over A. 3. Cos theta is adjacent all over hypotenuse, and from the figure we have, it means B all over C. The reciprocal of cos theta is sec theta, which now is the inverse of this, which is hypotenuse over adjacent, and that is C all over B. Number 5, tan theta is opposite over adjacent, which gives you A all over B with reference to the diagram above. The reciprocal cot theta is adjacent over opposite, which is B all over A. We can summarize the entire thing here using a mnemonic called SOHCAHTOA. So means sine, opposite over hypotenuse. C means cosine, adjacent over hypotenuse. T means tangent, opposite over adjacent. And of course, the reverse or the inverse of that are the reciprocals of the respective trigonometrical ratios of sine, cosine, and tangent. One of the tools we are going to use in dealing with problems in trigonometry is the special angles. They are actually also called the surd equivalent of these angles. When we look at angle 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Sin theta, equivalent, where theta is 0 degrees, so sin 0 degrees is 0. Sin 30 degrees is half, or 0.5. Sin 45 degrees is 1 over root 2, or root 2 all over 2, if you rationalize. Sin 60 degrees is root 3 all over 2, and sin 90 degrees is 1. Cos 0 degrees is 1, and cos 30 degrees is the complement of sin 60 degrees, which is root 3 all over 2. Cos 45 degrees is 1 all over root 2, or root 2 all over 2. And cos 60 degrees is half. Cos 90 degrees is 0. Now, tan 0 degrees is 0, tan 30 degrees is 1 over root 3, tan 45 is 1, tan 60 is root 3, and tan 90 is infinity. We call this infinity. Another name for that is undefined. It's undefined. Now, I want you to also observe that tan theta is the same thing as sin theta all over cos theta. This is an identity which we sometimes use in solving problems. If you look at what we have, the table we have above, tan theta, which is 0 here, means sin theta divided by cos theta, 0 divided by 1 is 0. If you divide half by root 3 all over 2, you have this. If you divide 1 over root 2 by 1 over root 2, you have 1, and so on and so forth. But the division by 0, 1 divided by 0, is undefined, is infinity. There are no real values for that at this level. Examples. Number 1. Here is a diagram describing a triangle, and you have the dimensions of the triangle indicated. As you can see, we are required to find the value of the unknown sides in the figure above. What are the unknown sides? S, Z, and Y, or S, Y, Z. Our solution, let's take the first triangle. And then we have here our S, we have here our 3, we have here our 4. We will not deal with this by using Pythagoras rule. And that says that the square of the hypotenuse is equal to the sum of the squares of the other two sides. So we square this. 3 squared is 9, 4 squared is 16, and that will give you 25. Therefore, your S is equal to the square root of 25, and that will give you 5. Now that you have known that, the next is for us to find the value of Y and the value of Z. So we can still look at it from the triangle. We can see that, let's take another triangle. and this is your 3, this is your 4 plus y, and then this is your z. With the diagram, this angle is already known. You can forget about this new y. With this relationship, you can find the value of z. So how do we find the value of z? Opposite over hypotenuse. Remember that this is a right angle. So where's our opposite? 3 all over z is equal to sine of 30 degrees. And sine 30 is half. Z will multiply 1, cross multiplication to give you z. 2 will multiply 3, and that will give you 6. So you have find the value of z. Now we can include our 4 plus y here. Our interest now is to find the value of y. You can also say 3 all over 4 plus y is equal to tan 30 degrees. Opposite over adjacent, tangent. Or you can say 4 plus y all over 3 is equal to cot 30 degrees. So we cross multiply, we have our 3 will be equal to 4 plus y times tan 30. Tan 30 is 1 over root 3. Or if you are using the cot, it means that 4 plus y all over 3 is equal to cot 30. And what is the value of cot 30? To be equal to root 3 because it's reciprocal. Now let's see what happens in this case. This one we cross and multiply. 3 root 3 is equal to 4 plus y. Therefore y is equal to 3 root 3 minus 4. If you are using this, you cross multiply. 4 plus y is equal to 3 root 3. Therefore y is equal to 3 root 3 minus 4. Both will give you the same solution. So the answer to the problem is this, or in other words, the same thing with that. You will have found the value of y. Therefore, your s, which you find is equal to 5, your y is equal to 3 root 3 minus 4, and your z is equal to 6. So these are the values of the unknown sides. I want you to note this, that complementary angles can be used to solve the problem as well. So what we have in this place, we have that 4 plus y all over 3 is equal to tan 60 degrees, because 60 degrees is the complement of 30 degrees. So when you solve it this way, you now have that 4 plus y is equal to 3 times root 3. So that your y is equal to 3 root 3 minus 4. The complement of 60 degrees is 30 degrees. Actually, where this is coming from now is that, remember that originally what we wrote was 3 all over 4 plus y equal to tan 30 degrees. But because what we are looking for is at the denominator here, we can also write this, the inverse of this one, as 4 plus y all over 3. Then the complement of 30 degrees is 60, and we write tan 60 degrees. The situation will remain the same, but it's more simplified because the unknown is at the numerator. It's always easier when the unknown is at the numerator, except where it is not possible to do that. Then you can solve and then simplify as usual. Example number 2. Given that tan s is equal to 4 by 3, find cos s. Our solution: sketch a right angle triangle and then this is your angle S, opposite over adjacent, and then of course we can find this side. Let's call it our L. So you have that L squared is equal to 3 squared plus 4 squared, and that will be equal to 9 plus 16, and that is 25. And our L is equal to the square root of 25, and that is 5. This is your Pythagoras rule from Pythagoras. So now that we have done that, we can therefore write our cos S, which is adjacent all over hypotenuse, and that is 3 all over 5. And that is the solution you are asked to find. Example number 3. If cos S is equal to the square root of A all over B, find cosec S. Solution. Recall that cosec S is actually equal to 1 all over sin S. Alright. Now, if our cos S is given to us, cos S is equal to A all over B under square root. Okay. Now, if you square both sides, cos squared S will give you A all over B. Then we also have that our sine squared S plus our cos squared S is equal to 1. In this case, our sine squared S is equal to 1 minus cos squared S. That means 1 minus A all over B. And that will eventually give you B minus A all over B. So our sine S will be equal to the square root of B minus A all over B. B minus A all over B. Therefore, your cosec S, which is equal to 1 all over sine S, will be equal to B all over B minus A, everything under square root. So your cosec S is equal to B all over B minus A, all under square root. Alternatively, we can solve the problem as follows. Here you have cos S equal to root A all over root B. Remember, solved application. Now, we sketch a diagram to represent this. This is your right angle, and this is the angle S. Adjacent over hypotenuse defines a cos. We don't know this side. Let's call it P or Y. Okay, let's call it P. So we now see that our P squared is equal to root B squared minus root A squared. And this becomes B minus A. Therefore, your P is the square root of B minus A. And then we can find our sine S to be equal to opposite, which is P all over root B. And that means our B minus A under square root all over root B, which can eventually be written as B minus A all over B, everything under square root. But we're talking about the cosecant of that, cos S, which is the reciprocal of this one. And that becomes B all over B minus A, and everything here under square root. This again gives you the same solution. We have example number 4. If tan B is equal to 5 all over 12, where B is an acute angle, evaluate cos B all over sin B plus cos B. Your solution. Now, usually it is better to sketch a right angle triangle representing the information And we have the angle B here. Tangent means opposite over adjacent. In other words, we need to find the hypotenuse. And let the hypotenuse in this case be S. So our S squared is equal to 5 squared plus 12 squared. And that is 25 plus 144. And that is 169. In other words, our S is the square root of 169. And that is 13. Now that you have known the value of 13, you can therefore write your cos B is equal to adjacent all over hypotenuse. And then you have your sin B is opposite all over hypotenuse. Substituting them in the given expression, cos B all over sin B plus cos B will be equal to 12 all over 13 all over 5 all over 13 plus 12 all over 13. Simplifying the denominator, because their denominators are equal, 13 and 13, you add the numerator. 5 plus 12 is 17 all over 13. And of course, this becomes 12 all over 13 times 13 all over 17. Division becomes multiplication, and you invert the element in the denominator. 13 and 13 will go, leaving you with the result 12 all over 17. And this is the solution to the problem.